Hello, everyone. Well, I think we should start now because it's already time. Well, maybe I should wait for 1 more minute. Okay, so remember, so can anybody hear me? Or if you cannot hear me, let me know, okay? It seems that it's okay because, well, okay, so since, well, 1 week ago, we discussed some very abstract group theory, right? Like, well, what is a normal group or normal subgroup? And also we introduced some really fancy terms like the stabilizer or centralizer and this kind of thing, right? And also we have this kind of group action or something like a group representation, this kind of stuff. And again, there are a lot of fancy words and it may make you confused, and something like the orbit and well, the index or this kind of thing. Okay, and we introduce a lot. Today, what we are going to do is we are going to make a very important application of this kind of thing. We are going to discuss using the group action to trying to find something about normal subgroup, trying to find something about the group structure, okay? So that you will see some very typical method about studying the structure of finite group, okay? And this is so-called the Sylow theory. Before we start, I just want to say this again. So, any question? Any question? So before we start, I just want to repeat this. If you do feel anything that you don't, well, it's not clear for you, or you have some concept, some terms that you don't remember, that's quite normal, okay? That happens all the times, especially in this kind of abstract algebra, because we introduce a lot of new terms. And although these terms sounds very fancy, but after all, it's just something that to make life easier, okay? To make our argument a little bit shorter. But for in OR, it's just something you already know. And we just use some abbreviation, something like abbreviation, to make the argument slightly shorter, okay? So if you forgot anything, if you think something is not so clear, just let me know. Just stop me and I can explain it to you again, okay? So it doesn't matter. And it's very useful when you try to learn this part, okay? Any question? Any question?
Sorry, can you like explain the meaning of group representation once more?
Of course. So you see, the group representation or group action is basically you have a group, okay? And this group can acting on some set. That means there is, well, for each element of this group, it can be seen as some kind of, well, some kind of map on this S, which is something like, well, an automorphism, something phi in automorphism group of this S, okay? Or in some short terms or in some particular examples, we just map G to something like the permutation group of S by something very naturally to be G maps to, well, an operation. This operation we denote it as G times S, which is something like GS or some kind of permutation acting on this one element in S. Okay, as S is in S. So this G can be seen as a very, well, maybe a small subgroup of permutation group of S, and this forms a homomorphism. And this kind of idea or this homomorphism can be seen as a representation of group, or somebody called this subgroup of permutation group to be the representation group, representation of your group G. Okay, so basically a representation of a group is something like what kind of a structure, what kind of a subgroup you can find on the permutation group can be seen as, well, your original group. Okay, this is so-called the permutation representation. Or there is another thing so-called the linear representation is you try to map your abstract group. It could be anything to the general linear group, which is a matrix. And then I believe you have already seen this kind of example on your homework. For instance, you can see that, okay, I gave you some subgroup of the general linear groups, like something like, well, 1, 1, 0, 0, 0, 1, 1, 0, and so on, this kind of group, and with plus or minus sign here, I guess, and so on. And you can see that this group can be seen as a linear representation of the, well, this quartering groups, right? Which is formed by plus or minus 1, plus or minus I, plus or minus j, plus or minus k. And it satisfies some condition. Okay? And this kind of thing is a linear representation, which is you're trying to find a subgroup of a known group, of a well-known group, so that this subgroup has the same structure of this well, arbitrary G. This is like a representation. Okay? And the good thing here is, as a group action or group representation, it can tell you a lot of things about S. Like you can try to divide S into some orbit, and all the orbits are just will have some number of the elements in S which can divide this G. And also the something like the fixed point, well, it's a subgroup of G, and something like the stabilizer is also it's a subgroup of G, and it can be, well, so that the number of the stabilizer of the orbit of S can also divide the number of the order of G, and so on. This kind of thing. And today you will see how this kind of trick can give you some magic result. Okay, as long as you can get some smart choice of the group action, you will get some amazing result. This is what we are going to talk sytoday, which is so-called the Sylow theorem. Sylow theorems. Okay, so let me first state this kind of theorem to you. The Sylow theorem more or less like the converse of the Lagrange theorem. Although we know that the converse of Lagrange theorem is not true, but Sylow theorem just tell you, okay, although it may not be true, but how far we can go if we want to find something like the converse of Lagrange theorem. The Lagrange theorem is, okay, the subgroup of a group must have order which is a divisor of your order of G. Okay, now the converse may be, what if we have a divisor of G and whether we are able to find a subgroup of this order or not? In general, no. But the Sylow theory tells us in some special situation, you could. Let me first state the first Sylow theorem. Okay, there are 3 Sylow theorems, and let me first say the most basic one. before that, let me give you a definition about what is a Sylow subgroup. If let's say G equals to N and P to the alpha is the largest power of P dividing N, which means P to the power alpha divides N and P to the power alpha plus 1 does not divide N. Okay, so if you make a factorization of N, you'll find there is a P to the alpha factor on the factorization. In some literature, this kind of thing, P to the alpha divides N, but P to the alpha plus 1 does not divide N, has a notation, although this notation is not a common notation, but in some literature, they do use that. It's P to the alpha, well, double vertical line N, okay? Not very usual, so, but if you do want to use it, I also agree with you, and it's also fine, but I hope if you want to use this notation, you can make an explanation in the future, okay? Because it's not very common. So then P to the alpha is the largest power of P dividing N. We call a subgroup of order P to the alpha, a Sylow subgroup, Sylow P subgroup. Because for a group, there might be Sylow 2 subgroup, Sylow 3 subgroup, something, right? So for this kind of group, we call it, of order P to the alpha, it's a Sylow P subgroup. Then, for instance, if you have a group of order 56, if you have a group of order 66, 56, then a subgroup of order 8 is a Sylow 2 subgroup. Okay, a subgroup of order 7 is a Sylow 7 subgroup. Okay, I think this is very easy to see because this 56 is equals to 7 times 8. So 7 only have power 1, 8 is 2 to the power 3. Okay. As long as we can find this kind of subgroup, it is a Sylow something P subgroup. Okay. Then the theorem is, first, the Sylow theorem says that, well, Sylow P subgroup for an arbitrary group always exists. Well, Longchen, I think okay, that's fine. So if P is a factor of N, then there is a Sylow P subgroup. So at least for the greatest power, you do have a subgroup that has order P to the alpha or P to the R, whatever. Okay, and there is a generalization or another version of Sylow's one. And after we prove this Sylow theorem, you can try to adjust our proof and then prove this, a little bit stronger version of Sylow's one. It's very easy to prove that as long as you understand this proof. The proof is similar. Well, now let's suppose G is equals to N P to the power R, which means P to the power R is the largest power of P that can divide the order of G, okay? And let's say NP GCD, well, let's say this is M to make it, well, less confused than here, okay? Let's say GCD of M and P equals to 1. Then for all the constants, for all the integers from 1 to R, G has a subgroup of order P to the T. Okay? So this means for all the factors with with a single power of a prime number, this G, the group, will always have a subgroup of this order, which seems to be very strong as a converse, some kind of converse of your Lagrange theorem. However, this doesn't mean that the converse of Lagrange theorem is true again, right? For instance, well, again, this G's order is 56. Then we know that there exists some subgroup such that this subgroup has order 2, or some subgroup, this group has order, say, 4, and some subgroup, this group has order 8, and some subgroup, and this subgroup is order 7. This is a Sylow subgroup, Sylow 2 subgroup. This is a Sylow 7 subgroup. These are some subgroup, but we know that, well, there is no subgroup. Well, we cannot guarantee that there exists some subgroup of order 14, of order 28. This is something we cannot guarantee. But these are some order of subgroups that we can guarantee from Sylow's theorem. Okay. Any question before we prove this theorem? Any question? Okay. If no more questions, then let's just continue to show the proof. Okay, so this proof for Sylow 1 theorem, Sylow first theorem, Sylow second theorem, Sylow third theorem, you can see this kind of proof as something slightly more complicated than the theorem before. Okay, and they can somehow to be seen as a little bit more complicated theorem. Okay, the reason I say it's slightly more complicated just based on the definition of a hard problem given by Moncrief, which is I don't know how many of you, I think some of you would like to take the topology seminar, and Moncrief in that topology textbook say that, okay, what kind of problem could be seen as a hard problem? Well, you can claim that those hard problems could be seen, okay, the best student of his cannot really solve it after they know all the definition, all the propositions of this books, of this area, but still they cannot get the proof easily. They cannot get the proof by themselves. Then this kind of problem could be seen as really hard problem. Okay. Other than that, well, we shouldn't consider some problems to be hard. Even for this proof, I can only say it's a little bit complicated, but if you try hard enough, I believe you guys can get the proof of this theorem by yourself as well. Okay, you may take a long time to get the proof of it, but I believe all of you are able to get the proof. So, well, let's see. It's just the problems of time, not a problem of a problem. Okay. So, oh, by the way, I'm sorry. There is another corollary of this Sylow's first theorem, which is so-called the Cauchy's theorem, which state like this: let G be a finite group of order n. Suppose P is a factor of n and P prime. Then the conclusion is there is an element A in G of order P. Okay? Be careful here. It's of order P, not P to some power. Okay? You can only guarantee that there is an element of order P. Not P squared, not P cubed, not P to the alpha, just of order P. Okay? Let me first maybe show the proof of this Cauchy's theorem. Okay? The proof is quite easy as long as you have this Sylow's first theorem. Say you have this G. You have a group G, and well, this G must have a subgroup H, and such that H is well, Sylow P subgroup. Okay, and let's say H in H. Well, then we know that if H not equals to the identity, we must have this H as order, well, P to some power. Let's say P to some power, or let's not use E, P to some power S. Okay, because the order of an element must be a divisor of your group. Okay. So then we can choose A to be H to the power P to the S minus 1. It has order P. Okay, so you can see that we cannot guarantee that, well, there must exist some element of P squared, of order P squared, or higher power of P. But we are able to guarantee that there is some element, such there must be an element of order P. Okay? So which also means there must be a cyclic subgroup of order P. Okay, for this group. Any question? Then let's try to prove the Sylow's first theorem. Okay, Sylow's first theorem, and in order to prove it, what we are going to do is we will try to use some group action smartly. So let's say n is equals to P to the alpha times m. Okay, and P does not divide m. Let's consider the action of G. Acting on, well, action, we mean, well, the action here, we mean we use G to acting on some set by, you will see, naturally by left multiplication on the set S, which is all the subsets of G with P to the power alpha elements. be careful here. This S is just a set of subsets. Okay, it's of course the subset will not be a group. It may be a group, but it may not be. Okay, so here what we do want is, well, by the way, so this left multiplication action is just you have some element a1 until a p to the alpha in S. This is a subset of G, so this is well, this is an element in S. Okay, then G in G, G act on the C is equals to GA1 and GAP to the alpha. Okay, then this is an action. Now what we do want is, well, could we by this kind of actions, and then we find that some element in S is actually a subgroup instead of a subset. It is actually closed under the group operation, this multiplication. But well, eventually, it happens that eventually we don't really prove that some element in S is actually a subgroup. Eventually, what we proved is some stabilizer of element on S is a subgroup. And it has the element exactly equals to p to the alpha. Okay, so let's try to see what we can find if we use a group acting on S. Okay, so first, if we, well, first we know that the total number of this set is n choose p to the alpha. Okay, and we also know that if we use a group action on this set, we basically separate this set into different orbits. Right? So which means we have this decomposition, well, of the number of this set, of the number of elements of this set by orbit. Distinct orbits, the number of your orbits. Okay, and moreover, we also know that means we decomposite a number, this number, into some numbers that is a divisor of, well, that is a divisor of G or N. Okay. Now, what we can say is a little bit more than that. We can observe that the total number of elements of S is some very special number. We have a lemma, say that this number is really a special number such that P is not a factor of this number. Suppose P prime and the GCD of MP equals to 1. Then P to the power R minus T is a factor of M times P to the R, you choose P to the T. T equals to, well, but P to the power R minus T plus 1 cannot divide P, well, M times P to the power R, choose P to the power T. T equals to 0, 1, until R. Okay. For this lemma, I will not prove it here. This is actually an exercise in your homework. And well, it's actually a stronger version of the exercise of your homework. If you try to prove this one, then what you can do is you can use an induction on T. Okay, This is a homework problem. This is a stronger version of the homework problem. You can use this way to prove your homework problem, or you can also try to find your own way to prove your homework problem. But whatever, then by this lemma, we know that P does not divide n choose P to the alpha. Okay, because n is P, well, m times P to the alpha, here is P to the alpha, so it almost cancel everything like P to the alpha, so there's no factor P anymore. Then let's try to look at this equation. It's a very important equation. We know that P is not a factor of the right-hand side. Okay? So that means, okay, P is not a factor of the right-hand side, but we know that this kind of thing, it is something. It is something, well, such that if you write G to the n, where G could C to be the stabilizer of C, then we know that this G C times the number of your orbit, number of the element of your orbit, is equals to the number of your whole group. Okay, so that means G C is equals to, well, n divided by the number of your orbit of C. That's it, the orbit of C. So on the right-hand side, you have a number that is not a factor of P. This means some of the numbers on the right-hand side could not be a factor of, could not be a power of P. Well, could not be the multiple of P, I'm sorry. Right? P does not divide this side. So that means you cannot have everything on the right-hand side is has a divisor as P. So that means there exists some C. Let's say C, well, C 0, such that the number of this orbit does not divide P. Okay, so that means the total value of GC is equals to what? Is equals to this n divided by this number, which is, well, you divide something that is not a divisor of P, so that means you don't hurt this P to the alpha. It should be P to the alpha to some power. Okay, so it's greater or equals to, well, P to the alpha times something, I'm sorry. P to the alpha times something, so it's P to the alpha, it must be greater or equal than P to the alpha, or GC can divide P to the alpha. Okay, that clear? You can find one element, you can find one number such that it cancels this, the other part of n, which is not power of P. So of course, the number of your stabilizer is greater or equal than P to the alpha. That clear? Then, we already know that P to the alpha divides GC, or GC 0 is greater or equal than P to the alpha. Now, if we want to show, as we mentioned before, this stabilizer, first is a subgroup. Then if we can show that this g c0 is less than equals to p to the alpha, then we are done, right? So now the problem is how we want to show g c0 is also less or equal than p to the alpha. How can we show this? Well, this is not so easy, but let's look at c0. Okay, so c0 is something, let's say a1, a2, until ap to the alpha. It's something. We know that this g c0 is actually a stabilizer. So let's try to, it's a stabilizer of c0. So let's try to take another version of this stabilizer to see how does this g c0 acting on, for instance, one element of this c0. Okay? For instance, let's try to see this one, say a1. Okay? It's equals to all the element multiplied by a0, by a1. And this g is in g c0. Since this g c0 is a stabilizer, so all the elements multiplied by this a1 must be something here, right? So it's a subset of c0. That clear? So which means if you have this g c0, you acting on, well, some element here, then what you will find is if you multiply something like a a1, then this a1 may move to a3, then it may move to a14, and so on. But whatever you make, you will eventually close this cycle by, well, by G1 in this group, G2 in this group, and G3 in this group. And then eventually, after you use all these kind of things, eventually it will go to something. Okay, it will go to, for instance, a 100. Then this something, whatever it is, it will all be a subset. It will all be a subset of this c0 because your G is a stabilizer of the c0. Okay, G c0 times c0 is always c0. Okay, that clear? So we are done. Because you know that G1 A1 equals to G2 A1 means G1 equals to G2. So that means G c0 acting on A1 has the same element as G c0, which is something, since it's a subset, it is less than or equals to c0, which has the element totally p to the alpha. So we get g c0 is less or equal than p to the alpha. So g c0 has element p to the alpha. Okay. So we have finished the proof. We find a group of order p to the alpha. You see, we use almost nothing, but we just take a group action. We just take a group action and try to analyze the orbit and stabilizer and so on. Right? Any question? Any question before we move on?
Why is the elements of the stabilizer smaller than the elements of the set itself?
Well, you see, this element of stabilizer, we can act in it on one element of this set, right? Then we know that, okay, all the elements acting on it will not change. Well, this element, after you use all the element to heat it, then it will still be on C0. Okay, so which means this set, not the stabilizer set, this set is a subset of C0. It just forms something, and if you use G's element to acting on A again, then eventually it will not get rid of this set, right? Because G is a stabilizer. Then that means, okay, as long as, well, we know that the element of this set is not a group on this set, the element of this set is the same as the element, the total number of elements of G C0. Because different, well, if you have different element of G C0, you will have different element on this G C0 A1. So these two have the same amount of element. But this element, this is a subset of C0. Okay, so it's greater or equal than this. That clear?
Yeah, clear. And another question. On the former page, why the elements in G C0 is larger than P to the power of alpha means it's equivalent with P to the power of alpha is divisible by G2.
Because this is a subgroup, right? And you know that the bottom will n equals to m to the power, well, m times p to the power alpha. The bottom has no factor p, right? So, which means it's actually equals to m over this guy times p to the power alpha. M over this guy is an integer. So it's greater or equal than p to the alpha.
Okay, thank you.
And of course, since GC0 is actually a subgroup, so yeah, it must divide this p to the alpha. Cannot be anything else. Okay, any other question? Any other question? Okay, so if no more questions, then let's see some examples. Well, maybe we will postpone our example slightly later because the Sylow's first theorem is just some theorems that, well, not really some, it's really fundamental. It's very fundamental because it tells you the existence of this Sylow T group. But sometimes it's not really useful because, well, I cannot really say it's not useful, but it's not really useful when you're trying to use it to do some classification of group. So before we do these examples, let me mention what is a Sylow's second theorem and Sylow's third theorem. And then I'll provide you some examples. This is really something very practical. That is, well, all the Sylow P group all the Sylow P groups are congruent, are conjugate to each other. Which means if you try to use this, well, use G acting on the set of Sylow P group, and this action is by taking this conjugate of each group, then eventually this action is actually transitively. Okay, you only have one orbit of this action. And the number S of Sylow P subgroup divides n is a factor of n. How many Sylow subgroups you have? Well, we don't know, but we know that it's a factor of n. And satisfy S mod P equals to 1. It must be able to write as Kp plus 1 for some k. Okay? So we have a very good description about how many this kind of subgroup you could have. So this is something interesting because, as before, other than list all the subgroups, we don't really have any idea to count how many particular type of subgroup you have for a group. Okay? So let me write a corollary to this Sylow second and Sylow third theorem, and then I'll provide you examples about the application. The corollary is, well, since all the P subgroup are conjugate, that means if you have a Sylow subgroup, then if we want it to be normal, if we want H to be normal, it happens only if this G only have one Sylow subgroup, Sylow P subgroup. Okay. Let me show you, well, why this kind of theorem sounds very magically, but it's also useful. Okay. For instance, we can, based on this theorem, show that every group of order 15 is cyclic. Why is that? Can we imagine how could we show this this statement? Try to imagine how we can prove it. By this kind of Sylow P group, how could we approach it? Where should we start? Every group of order 15, it must be a particular type. Why is that? How can we start? How can we start? Any idea? Any idea? Well, maybe I should ask you first. So it's a group of order 15. So what could we know about Sylow subgroup of this group?
It has only one Sylow 3 group and a Sylow 5 group, each one.
Yes, that's right. So we know that 15 equals to 3 times 5. Okay, so we know that, well, okay, it has, well, G has a Sylow 3 subgroup as well as Sylow 5 subgroup. Okay. And how many Sylow 3 subgroup does G have?
Only one.
The number should be 1. Why should it be 1?
Because it should be it should divide in, and the remainder of S taking modular 3 is 1. So so this could only be 1.
That's right. Suppose it has let's say S Sylow 3 subgroup. Suppose it has S. Then we know that S divide 15 and S mod 3 equals to 1. Right? So the only factor of 15 is 1, 3, 5, 15. Among them, which one mod 3 equals to 1? Well, it's only 1, right? So S equals to 1. Similarly, G only have 1 Sylow 5 subgroup. Okay, so that means a lot. That means, well, you have only one Sylow subgroup, Sylow 5 subgroup, you have only one Sylow 3 subgroup. Then the conclusion is, let's say H, Sylow 3 subgroup, and let's say K, Sylow 5 subgroup. We know that they must be normal. Right? Otherwise, well, you can see from this corollary. Otherwise, they must conjugate. There must be some conjugate of this group. It's not equals to it, but it's also a Sylow subgroup. You have more than one, which is a contradiction. Okay, so you have two normal subgroups. What can we say about the intersection of H and K? What can we say about the intersection of H and K?
Empty.
It's not empty, it must be trivial, right?
Yeah, it has identity.
Yeah, why is that? Why it must be why it must be this trivial?
Because if like say some of the elements they are in the I mean other than the identity, they're in the intersection of H and K. That means that means that when we're taking the conjugacy of this element is also in H and also in K.
So then, well, what's the contradiction? Well, you can imagine. Well, this is not so hard to see. You can just imagine. So the element in H, other than identity, what's the order of that? The order must be 5, right? How about K? Well, the order must be 3. And the element in K, other than E, must have order 5, right? So that means the intersection must be an identity. Or if you do not like this, then you can also say this intersection is both a subset of a subgroup of K and a subgroup of H. Then we know that then it must be a divisor of 5 and 3. So that means this must only have one element. Okay. And well, what we can say about H times K? What we can say about H times K? This is a little bit harder, but we also mentioned it. We also mentioned it last week on Thursday. If we have two normal subgroups, we do the multiplication.
Yeah, the elements in this group was like the elements in H multiplied the elements in K and divided the elements in the intersection. So it's 15. You mean something?
Yes, it will. The number of this element must be 15. Or you can also try to compute it without that formula because we didn't prove that formula. You can also say that, okay, this is actually a subset of G. Okay, but we do know that HK, K is a subset of it. H is also a subset of it. It's actually a subgroup of it. So which means, and it's actually has more element than K. Because first, all the elements in K are in this set. Second, at least one element in H are in this set, are in this subgroup. So the number of HK must be greater than the number of K. Okay? Because K is a subset of HK because H contains E, right? H is also a subset of HK because K also contains E. So we must have, it contains both elements on K and both elements on H, so it must be, contains more elements than K. But it's also a subgroup of G. So which means it divides 15. Then that means it's greater than 5, so that means HK is equals to 15. That means HK must be equals to G. Okay, then we can quote the theorems we have learned before. HK are both normal subgroup, and the intersection is only identity. The multiplication is equals to G, then that means it's isomorphic to H cross K. Okay, which is, Z3 cross Z5, which is isomorphic to Z15. Okay? This is how we can do something like a classification of groups by using the Sylow theorem. Any question? Any question? Okay, so then let me show you one additional example. This example do something similar as we did for the previous example. That example is 15, order 15 group. What if you have a group of order 14? Well, this example says that based on the Sylow theorems, we know that the group of order 14 is isomorphic either to Z14 or to D7, which is a group that I think this is so-called it's so-called dihedral group. Dihedral group of order, well, the seventh dihedral group, okay, which is a group that is really useful when you study geometry, and I believe you also see this group when you're doing your homework this time. It's this type of group, x, n, y, m, with x to the power 7 equals to e, y to the power square equals to e, and x, y, well, yx, y inverse is equals to x inverse. This kind of group. Okay. Let's prove it. Again, if we want to show this kind of theorems, the easiest way to find is how could we classify this group is we try to find some normal subgroup and then see whether it's this group is isomorphic to the multiplication, the product of this two normal subgroup or not. If not, then we will see some other method. Okay. So how could we prove it? Well, first, let's try to use the Sylow theorems to see how many Sylow P group it has. Again, G has order 14 is equals to 2 times 7. Okay, then we need to discuss how many Sylow 2 group does G have, and how many Sylow 7 group does G have. What can you say about this? What can you say about this? Any idea? So how many Sylow P group does it have? Sylow 7 group. How many? Anybody can tell me?
Two.
Why is 2? So what can we say about the number of Sylow 7? Well, maybe how many? Well, how could we say about this number?
Well, you break it down into Sylow 2, Sylow 7, and right?
Well, we have these theorems, right? What can we say? What can we say about it? Sylow P groups, this number must divide n, and mod P equals to 1, right? Let's say this is S, then S is a factor of 14. S mod 7 equals to 1. This is what Sylow theorems tell us, right? What kind of S could you have?
Only one?
Yeah, you have only one Sylow 7 group. And it's actually normal, right? That's easy. Well, at least not so hard, as long as we can read this Sylow theorems. Okay. How about Sylow 2 group? How many Sylow 2 group does it have? Any idea? Any idea?
Do we do like the same thing again?
Yeah, we could definitely do the same thing again, right? So we know that this number of Sylow 2 subgroup, let's say it's t, okay? T is a factor of 14. T mod 2 equals to 1, which means G is an odd number. Okay? What does that mean? That means G equals to 1 or 7, right? Come on. I believe everybody can solve this problem. This is 14, right? It's not some big number. Try to find the odd factor of 14. It's not a problem for you. So there are two situations when we're trying to do the classification of 14 order group. One is you have one Sylow P group with Sylow 2 group. Another one is you have 7 Sylow 2 group. Yes, and it also wants us to show, okay, it's either this or that. So case 1, if, well, only one Sylow 2 subgroup, then we are done, right? This G is isomorphic just as before, just as the previous problem. It's isomorphic to Z14. Okay? But how about case 2? If it has 7 Sylow 2 subgroup, well, this will be slightly harder than we thought, because what if it has 7? Okay, then let's list them. Let's say it's H1 until H7. Are the 7 Sylow 2 group? Well, then, okay, this group, at least there are 2 groups, so it's not so hard. It only have E and one other element, right? Let's say it's generated by, well, say H1 is equals to E and C, okay? And C squared equals to 1. And K is the Sylow 7 subgroup. Since it's a 7 subgroup, so it's a cyclic group. Let's say rho generated K. Okay? So K is equals to E rho squared until rho to the 6. Okay? Then let's consider rho to the power I, C rho to the power minus I, which is you take the conjugate of this guy. What you find is you have there are totally 7 different for I from 0, 1 to 6. Okay, there are 7 different elements. There are 7 different elements of order 2. Okay. So that means, well, correspondingly, you have all this kind of element are the generator of this H1 until H7. Because you only have 7 order 2 elements generated, well, 7 Sylow 2 subgroup. So we find those 7 different order 2 elements. So they must generate at H1 until H7. Okay. So probably that's what we need. And well, let's consider this element. Now we more or less think this row must be over X. This C is order 2, should be over Y. So let's try to consider this C inverse row C row C inverse. If it equals to rho to the power -1, then we are done. Because we find all the elements and it satisfies, okay, rho to the power 7 equals to E, C square equals to E, and it's equals to this guy equals to rho to the power -1. Then we are done. Right? So let's try to compute it. And we know that this K is a normal subgroup. So if you take this kind of conjugate, it must be another element on K, because C inverse is equals to K, right? So this kind of conjugate can only change it to something like rho to the power J for some J. Now the problem is, what should be over J? Well, let's consider this one. Rho is equals to, because C square equals to 1. Let's consider rho, write it as C square rho C to the power -2. It's equals to, you take the conjugate twice. And for once, you get rho to the power J. So for twice, you get rho to the power J square. Okay. So what we know is J square mod 7 equals to 1. That's great, because we try to imagine this J is -1. Then you find that this J square equals to 1 mod 7. That means J could only be 1 or -1. That means C inverse is rho to the power -1. It cannot be 1. Otherwise, this G is a billion, and G is actually, well, isomorphic to Z14. Very easy to see. Then we know that. So that means G is isomorphic to D7. Yes, somebody asked me about how you can justify, okay, you have this kind of, you have this kind of relation of your 2 generated elements. You have this kind of relation, this relation, and this relation for your 2 generator of your group. Then how can you say this group has a unique structure? Unfortunately, this semester, we don't have time to tell you why this group has a unique structure for this kind of xy, such that x7 equals to e, y squared equals to e, and yx, y inverse equals to x inverse has a unique structure. But if you want to know, you can try to check it yourself. This is something about the free group and generator and relation. It's in Arting's book. You can try to check it, and then you will see why, as long as we can check this relation satisfied, well, we have this group is the same group it has a unique structure. Okay, you can check it on Artin's book. I think it's on the more group theory chapter, last section. Okay, so we prove that a group of order 14 has two particular structures, cannot be more. Okay, let's have a 10 minutes break, and we'll resume at 26. And next, after we resume, we'll prove the Sylow theorem, Sylow second theorem, and Sylow third theorem. Okay. Let me pause. In this case, if you feel confused, that's very normal. But just don't forget, if you have something, some words, some terms that don't understand, that forgot the meaning, just ask. Okay, just stop me and ask. Maybe let's see one easier example. Okay, maybe an easier example. So how about this? Show that a group of order 56 will not be a simple group. So which means simple group, I hope you still remember the meaning of simple group. It means you do not have a, proper normal subgroup. You do not have a normal subgroup that is not the whole group, not E. Okay? How we can prove it. So the idea is the same. Suppose G is equals to 7 times 8. The idea is the same. If we do want to find some particular type of subgroup of a group, then, we should always refer to the Sylow theorem. And for Sylow theorems, we can use it to study the subgroup of a group, right? So let's try to find the Sylow subgroup, and if this Sylow subgroup have only one, then that means it is a normal subgroup. Then it is not a simple. This G is not a simple group. Okay, so let's try to see how many Sylow 7 subgroup does it have? How many? How many Sylow 7 subgroup does this G have? Any idea? How many?
Do we do like the same thing with like theorem about S when it should, like S should
Yes.
be equivalent to 1 modulo 7?
That's right. And we also know that S must be a factor of 56, right?
Yeah, and S equals to 8 kind of fits.
So S equals to 1 or 8, right? Okay. Now if S equals to 1, then we are done, right? Because if you only have one Sylow 7 subgroup, then that means it itself is normal, right? No other conjugate could form a group other than itself. So we are done. So what if S equals to 8? We already find, if S equals to 1, we already find a normal subgroup of G with order 7. So it's not a simple group. Now if we have 8 Sylow 7 group, it could be a problem, right? So how about this? then how many Sylow 2 subgroup does it have? How many Sylow 2 subgroup does it have? How many?
Well, there are a lot of possibilities, right? Because
There are a lot of, but is that a lot of? Well, again, T mod 2 equals 1, right? T is a factor.
oh no, wait, only 7, right?
Well, yeah, that's right. So T equals to 1 or 7. If T equals to 1, then we are done, right? Because we find a normal subgroup with order 8. Otherwise, T equals to 7 is another problem. Well, so the only problem now is, what if this group contains 8 Sylow 7 subgroup and 7 Sylow 2 subgroup? In this case, could it be a simple group? Let's see. Suppose you have this amount of, a lot of, well, Sylow 7 and Sylow 2 subgroup, okay? Then let's see what we have, okay, what we can get. First, if it has 8 Sylow 7 subgroup, well, that seems a lot, right? Then we know that if you have 2 Sylow 7 subgroup, they are both of order 7, right? If H1 and H2 are of order 7, what can we say about the intersection?
It's 0. Wait.
It must be this identity, right? Or H1 or H2, right? Because the number of elements must be a factor of H1 or H2, which means it's either 1 or the whole thing. So which means for all this 8 Sylow 7 subgroup, you must have totally how many different elements you find among this 7 Sylow among this 8 Sylow 7 subgroup. How many different elements could you find?
Wait, can you repeat the question, please?
Among this H1, H2, until H8, they are both subgroup of order 7. Then, how many elements can you find, for instance, on the union of all this subgroup?
Well, either 1 or 7, right?
Is either 1 or 7. So that means if there are 8 different Sylow 7 subgroup, then they can only, for any 2 of them, they only have 1 common element, right? So which means, how many do you have? How many different elements do you have? You must have 8 times 7 minus 6, right? You calculate this identity, minus 7. You calculate this identity element 8 times. Each one of them has 1. Okay? So totally, you have 48 elements, 49 elements, such that you have 1 element E and 48 elements with order 7. Okay, all the elements on these groups are of order 7 or its identity. Okay, that's a large amount of element, right? That means G has E and 48 elements with order 7. Okay, you already determined the order of 49 elements of G. But we have 7, well, order 2. I mean, you have 7 Sylow 2 subgroup, K1, K2, until K7. K1 has 8 elements, right? K2 has 8 elements. K7 also have 8 elements. Well, then how many different elements do you have on this Ki? We need to check the intersection of, for instance, K1 and K2.
Wait, sorry, I forgot. Why is this like K1 has 8 elements?
Because Ki are the Sylow 2 subgroups. What is the meaning of Sylow 2 subgroups? It means all the subgroups of order 8, right? So again, what can we say about the K1 intersect with K2? Is either equals to 1, or equals to 2, or equals to 4, or, well, it cannot be equal. K1 cannot equals to K2, right? They cannot be identically equal because they are 2 different Sylow P groups, Sylow 2 groups, right? So on K1, we have 7 elements with even order. On K2, we at least have 4 different elements of even order. The order of this element on K1, K2, and K7, other than identity, must have an even order, either order 2, or order 4, or order 8. Right? So totally, we got 11 more elements, at least 11 more elements. Of order, of even order, which is a contradiction, right? Because this G totally have 56 elements. It already have 48 elements with order 7. It cannot have additional 11 elements with even order, right? So G is not simple. Either S equals to 1 or T equals to 1. Okay? Any question? Any question? Any question? So you see, the method we use here are quite elementary. We even count how many elements on this group without any structure, right? But the key part is, again, we use the Sylow theorems to compute how many groups do we have. How many subgroups do we have, right? Then it can help us to understand a lot of things. Any question?
Well, I just wanted to go back and
Mhm.
because I kind of forget we say the group is simple because
Oh, the group is simple if G is simple if it has no normal subgroup other than E and G. More or less like well, more or less like this kind of the atom, right? Or a prime number. You cannot divide it into, well, smaller elements. You cannot divide this G into smaller element. You do not have the good structure of this G. Okay, this is the meaning of a simple group.
well, but then my question would be, so when we were doing like the operations with the group H,
Mhm.
they are already groups.
Yes.
Well, they are subgroups. So does it mean that G already have a subgroup?
Well, normal subgroup is not a subgroup, right? Of course,
Oh,
you will
yeah.
always have subgroup of a group. This is well, if you have a group that has no subgroup, then this will have a very huge restriction. Then probably your G will be something like ZP or something. Okay, but if we release it a little bit to say it's normal, it has no normal subgroup, then well, the problem becomes more interesting. Okay. This will be a difference.
Wait.
Mhm.
Wait, just to make sure. So which normal subgroup did we find in
We
the
find
end?
that either S equals to 1, if S equals to 8 and T equals to 7, this is impossible, right? So either S equals to 1 or T equals to 1. That's not this one. We find that either S equals to 1 or T equals to 1. Okay? If S equals to 1, that means you have a unique Sylow 7 subgroup, then it itself is normal. Otherwise, it has a unique Sylow 2 subgroup, it itself is normal. Okay? Because otherwise, if we take the conjugate, then we have another one. We have another, if otherwise it is not normal, that means we can take the conjugate to get a new group. But this new group is also a Sylow 7 subgroup or Sylow 2 subgroup. So it cannot be. You cannot get a new subgroup if you take the conjugate. Okay? Any other question? Okay, then let's try to prove the Sylow second and the Sylow third theorem. Well, maybe before that, let me repeat the theorems and well, let me repeat the theorems, okay, so that you don't forget. What is a Sylow second? What is a Sylow second theorems? Sylow second theorems say that all the Sylow P subgroups are conjugate to each other. Okay, this in some literature is called the Sylow second theorems, the second Sylow theorems. By the way, so there is another version of Sylow 2. which says that, okay, well, if you have this Sylow P subgroups, then you can actually, well, they are conjugate, but as long as you have some smaller subgroup, well, let's say G equals to MPR, and NP, GCD equals to 1, and P is, well, Sylow P subgroup of G. Then for any H is less than G, I mean, H is less than G, and well, I'm sorry, there's a mistake I think I made. I think there's a typo. Yes, I'm sorry. Yeah, sorry. So for any H is less than G, H is a P group. P group means the order of H is P to some power. I think we mentioned this before. Okay, then there exists some G such that GHG inverse is a subgroup of P. Okay, so which means in a Sylow subgroup you can get a smaller one. You can even get a smaller one, and after you take the conjugate, it's still well, as long as you have a P group, it's still a subgroup of this P. Okay, this is another version of the second Sylow theorem. And okay, so I believe you have you have a sense, you have some idea about the meaning of the Sylow second and Sylow third theorems. It just tell you that all the Sylow subgroup, all the Sylow P subgroup are conjugate, and we have, well, we can count how many Sylow subgroup we have. Let's try to prove it. Let's try to prove it. This proof is a little bit long because we combine the proof of Sylow second and Sylow third. Okay? So how can we show that all the Sylow P groups are conjugate to each other? Well, this is not so easy to think. So suppose you have two Sylow subgroups. Suppose you have K and H, Sylow subgroups, Sylow P subgroups of G. Okay, then how can we show that they are conjugate to each other? That's not easy. Oh, sure. Yeah, so this is another version of Sylow second, which says that basically, well, even you have some P groups, it can be conjugate, it is conjugate to some subgroup of P. Okay, you have a Sylow P group, and you have a Sylow P groups, and then you have another P group. It will conjugate to, it can embed into some Sylow subgroups subscript. Okay, you can embed it on this Sylow subgroup. Okay, and don't worry if you forget, if you are not able to write it down, and I will scan everything and upload it so that you can still, well, get it. Okay. And this time, probably we will not use these theorems. We will use it to prove something on Monday. on Tuesday next week. Okay. On Tuesday, we are going to show more examples about how we can use the Sylow theorems to do the classification of groups. Okay. So again, remember what do we want? What we do want is we want to show that H and K, they are conjugate to each other, right? How can we show that they are conjugate to each other? Well, this is not so easy, but let's try to do it like this. Again, let's try to use a group action in a very smart way. Let's try to use K acts on G over H. Be careful here, this is just a set of cosets. It's not a group, right? It's not a quotient group because H is not normal. H is not normal, so this is just a set of cosets. But we can still use K to acting on it, right? Then what we know is, if we do it like this, we will have our counting formula. The number of G over H is equals to the summation of all the orbits, right? And what we know is the orbit, the number of this orbit is always a divisor of K, which is P to the alpha. But what is the number of G over H? The element of this coset is equals to the index of H, right? This is a definition. So it's equals to.
I think somebody wrote something in the chat.
Yes, I already showed that.
Oh, okay.
Thank you. So it is actually equals to what? By Lagrange is equals to this one, right? So it's equals to M. G equals to M times P to the alpha. H equals to, well, H has order P to the alpha. So it's equals to M, which co-prime to P. So same trick works here. On the right-hand side, it is not a factor. It has no factor P, right? But on the left-hand side, all the numbers are factor of P. So that means there exists something, something like OA, or maybe OAH, some orbit of AH, such that the number of OAH equals to 1, right? The number, the number of elements of this orbit must equals to 1. It cannot be P to some other power, right? Otherwise, on left-hand side is has no divisor P, right-hand side has. Okay. For some AH in G over H as coset. What does that mean? That means K acting on this AH, it has an orbit to be contains one element, right? So whatever K, this is K with left multiplication. Okay, so whatever K in K, K times AH must be equals to AH, right? Otherwise, the orbit contains more than one element. That means Ka, since your H contains identity, Ka must be an element of AH. Or K belongs to AHA inverse. We are done. For any element, it's on this set. So K is a subset of AHA inverse. But we know that the element of K is equals to the element of this set, which is P to the alpha. So K equals to KAHA inverse. Okay, so this proves the second Sylow theorems. This one, the first statement of our theorems. All the Sylow P subgroups are conjugate to each other. Okay, any question? Any question? No? Then let's continue. Okay, so now we want to show that the number of the Sylow P groups, it first divides n and it mod P equals to 1. Okay, well, let's first try to show that it's actually divides n. Okay, let's first try to show this, and then let's try to compute what is really S. This kind of thing, again, maybe we should try to find some different group action in order to find it. And since we try to compute the total element number S, so let's try to see the set of all the Sylow P groups. And let's try to use G, X on it, with conjugate. With conjugate operation, which means, well, G, an element in G, acting on a set, on a Sylow P subgroup, G acting on a Sylow P subgroup is equals to GKG inverse. Okay, we take the conjugate as an action. Then this is an action. So what we know is G is transitive by the first part, right? Because the first part just to say that if you use G to acting on this S by conjugate, well, everything will be connected. Any two of these Sylow P groups can be connected by some element in G by taking the conjugate, right? So which means you only have one orbit, which in some fancy word, G is transitive. This action is a transitive action. Okay? So we know that you only have one orbit and is equals to the number of S, the total number of this set is a factor of G. Okay? So if we call this number of all the Sylow subgroups to be S, then this S is a factor of G. That clear? That clear? Hmm?
Well, yeah, kind of.
Yes, so you can see this this kind of way is to take group action in some particular way. It's a very useful tool to help you do some counting. Okay, because when you try to do this kind of counting, you try to divide a set into different orbits, and these different orbits are always factor of your group G. This is something really useful, can help us a lot. So the last thing we want to show is this S mod P equals to 1. Okay. So how can we show this? This is, again, not an easy thing. So maybe we should change some other actions and see whether we can get something or not. Since we try to compute this kind of mod P stuff, then what we need to do is, well, for instance, H is a Sylow P subgroup. Let's try to use H X on S. The reason we would like to do it like this is because we want to consider the mod P property. So which means we want this guy, the group, which acting on our set, to be something like, well, order P to some power, which is why we would like to choose the Sylow P subgroups to act on S and see what happens. Okay? By the way, H is also an element in S. Instead of taking the whole G, we take a subset, a Sylow P subgroup. So we know that this little s is equals to the summation of different orbits. Let's say OJ, okay? That's good. Then we know that, okay, this OJ should divide H, which is P to the alpha. We want to show that S mod P equals to 1. That's very clear now. We want to show by this formula, we only want to show there exists a unique orbit, say OK, the number of OK equals to 1. As long as we can show this, we are done, right? Because the rest are just some power of P. That clear? Okay. So that means we need to consider in what situation you can have the orbit as only one element. Okay, let's say this O little k is an orbit of well, of say k in S. Okay. So let's see, what can we say about this? Well, if you want the orbit to equals to 1, what does that mean? That means, remember, this is so-called the centralizer, or it's another version of stabilizer of your element, of your element K. Okay, which is G over, G belongs to this whole group G such that G, K, G inverse equals to K. It's a centralizer, or if you want, you can also call it a stabilizer. It's stabilizer, because after all, it's kind of kind of the kernel of some action of capital K, right? If we know that this orbit contains only one element, that means Nk should contain e to the alpha element, right? Because we know that multiplication of these two guys equals to your action group, which is a number of G, a number of H, which is p to the alpha. Okay. And now what we will show is, okay, if number of OK equals to 1, then that means well, it's actually equivalent to say that if you use H to acting on, I'm sorry, this is a centralizer of this among this whole group G. So this Mk is equals to M times P to the alpha. Okay, or it's a number, total number of G. I'm sorry, we cannot really say this because these are two different operations. So I'm sorry, there's something wrong. We cannot really say anything about the size of Nk because it's more or less like this, well, the stabilizer of K on G, okay? The stabilizer of K on the whole group action G. But now what we consider is very smaller, it's a smaller group action. It's a group action, you use H to acting on it, okay? But moreover, what we can say is, if the number of the orbit is 1, then what we can say is, this H is, it must be a subset of Nk. Because if the orbit of K is 1, then that means all the elements of H you acting on K doesn't change it, right? Because your orbit is 1. So this means H must be in the stabilizer. It must be a subset of stabilizer. Okay? That okay? So we also know that well, your K is also a subset of Nk. Because whatever element in K, if you use this element to multiply K and multiply this element inverse, you still get K, right? You will not lose any element by using the element in K to acting on K, right? So that means, okay, H is actually a subgroup, as K is also a subgroup of Nk. Moreover, we know that H has element P to the alpha, K has element P to the alpha. So H and K are Sylow P subgroup of NK. Right? Because NK, whatever it is a subgroup. It's a subgroup of G. It is a subgroup of G, then of course it's well, the order of this the order of NK must be a factor of G. Since you have these two guys as order P to the alpha, then of course these two guys are P sub a Sylow P subgroup of NK. Okay, that clear? And what we also know is, magically, if you consider NK and K, K is actually a normal subset of NK. Why is that? Yeah, of course, if you use K multiply K by multiply by K inverse, it is equals to K for any element on this NK. So N belongs to NK, then NK and inverse is equals to K by definition. So which means K is a normal subgroup of NK. So that means K is a normal subgroup of NK. Meanwhile, it's a Sylow P group of NK. K must be equals to H. The Sylow P subgroup of NK must be unique. Since they are both, so that means H must be K as well. Okay, so that means the number of the orbit equals to 1 if and only if K equals to H. You can show the only if part easily. Well, that means there exists only one K. Well, there exists only one orbit, which is well, let's use OH, such that the order of OH equals to 1. The orbit of H under the action of H has orbit 1. Other than that, all the other elements on S will have order higher than 1. Okay, so S mod P equals to 1. Well done. Any question? I know this proof is kind of twisted, but if you try to check every steps, you'll find that the idea is quite clear. We want to find for what kind of orbit it has only one. Element. Then, of course, if this orbit is the orbit of this set by itself, then the orbit should be 1. Right? So then the only thing you try to show is, well, for other orbit, for the orbit of some other element, it must have something different. It must be the orbit has total number higher than 1, greater than 1. Okay, and then the idea is you try to find it as some Sylow P subgroup. For instance, as a Sylow P subgroup of your stabilizer. Then you find that, and you find that it's actually normal. It's a normal Sylow P subgroup, then it's unique. It cannot have any other options. Okay? Any question? Yeah, I'll wait for 2 minutes or maybe 3 minutes in order for you guys to ask questions, because the proof is not so easy. It's kind of twisted, and you can find that the group action here is really amazing. It tells us a lot.
Can you also like put the previous page nearby, because I forgot how it looked like.
Of course, that's it. Yeah.
Oh, thank you.
Mhm. So if you have any kind of questions, just feel free to ask. Because the first time to see this proof, you must well need some time to digest, and you must have some problems, because you guys, I don't think you are very familiar with a group action, since we just mentioned on Tuesday, right? You don't have any practice on group action. So basically, as long as you use a group action, the orbit and the stabilizer will become your friend. They are your friend simply because they are the factor of something that you already know. Okay? Okay, so any other questions so that we can discuss?
Just, oh, well, too many of them. Well, so again, when we do the orbits and we say that the number of orbits is 1, it's equivalent to saying that H is a subgroup of the centralizer, and I kind of forgot why.
Because, well, the orbit is just a 1. That means for any element on H, right? You take these conjugate operations, it gives you back to K, because you cannot get a new group. Otherwise, it's in the orbit, right? So which means HK, H inverse equals to K, right? And this centralizer or this stabilizer is actually the collection of all the elements such that GK, G inverse is K. So of course, this is a subset of it, because all the elements satisfy this condition. Okay.
And do you mind just like going through the main steps of the proof so we can like see the structure of the proof?
Sure, sure. So the main thing we try to do is we try to use an arbitrary Sylow P group acts on this set of Sylow P groups. Okay. The reason we try to do that is because we want to say something about modular P, right? And if you want to say something about modular P, then probably you want to find a group which only have the factor P to acting on it, so that you will know that everything we discuss are modular P. So which is why we use the Sylow P groups to acting on it. Then it divides this whole thing, this whole set of Sylow P groups into orbits. Okay, it divided into orbits. then each orbit a p to the alpha. So if we want to say that, okay, eventually you got this number modular p equals to 1, we want there exists only one thing such that the orbit equals to 1. Other than this orbit, all the other orbits are just p to some power. So then how could we find there is only one orbit? Well, you can imagine if you try to find the orbit, you use h acts on s. If you want to find the orbit of h under this action, then you find the orbit only contains one element, right? Because h acting on h, it cannot change h, right? So probably what we want to see is then, well, for any other group, for any other Sylow P groups, this action, this H acting on such kind of Sylow P groups will give you, well, will give you an orbit that is larger than 1. Right? So that's trying to do it. Then we try to find, okay, this is an action of H. But if we try to find this stabilizer of the action of G, then we find that this stabilizer contains both H and K. Because we know that, okay, H is a stabilizer, it has only orbit 1, the orbit is equals to 1. Well, and K is also the stabilizer of K, of course, right? K doesn't change K. Then what we want to show is now what if K equals to H? How can we show that if K not equals to H, this cannot happen? Then we find that, okay, for the stabilizer, K is actually a normal subgroup. K is a normal subgroup of it. Meanwhile, K and H are both Sylow subgroup of NK. So which means K must equals to H. Because a Sylow subgroup, if it is normal, then it's unique. Then we find that, okay, that means if K is not equals to H, this cannot happen. Well, H cannot make this orbit of K to be contains only one element. So we get that, okay, so that means there is only one orbit. Other than that, all the other Sylow subgroup will have different orbit. We have an orbit which has more than one element. And then that means, okay, you must have the remainder to be 1 if you merge P by this equation. Okay? Any other question? Any other question? Well, we only have 5 minutes left, so I don't really want to continue because we can do more application about this well, Sylow group theory, well, Sylow theorems, and but I think maybe I should postpone it to next time. Okay. Well, last time and the time before last, I just delay the class and make it slightly longer. So maybe I'll just let you go 5 minutes early today. Okay. So feel free to go. And on Tuesday, next Tuesday, we'll see more application on this group action and the Sylow P group things. Okay. See you next week.